Good afternoon, everyone. This is Sanjana Mezabin, Chairperson of IEEE BUET Student Branch WI Affinity Group and Vice Chair of IEEE BUET Student Branch. Here with me, I have Sattaki Bonik, Chair of IEEE BUET Student Branch, and Shakil Anwar, General Secretary of IEEE BUET Student Branch. It is our honor today to invite you all to this second Tech Talk of webinar series, Research and Innovation Challenges during COVID-19. This is jointly organized by IEEE IS BUET Student Branch Chapter, IEEE SPS BUET Student Branch Chapter, IEEE RAS BUET Student Branch Chapter, IEEE EMBS BUET Student Branch Chapter, IEEE BUET Student Branch WI Affinity Group, IEEE BUET Student Branch, and IEEE Bangladesh section. Let me introduce today our moderator, Dr. Celia Shahnaz ma'am. She is a senior member of IEEE and fellow of Institute of Engineers, Bangladesh. She is a professor of Department of IEEE BUET, Dhaka, Bangladesh. She is a chairperson of IEEE Bangladesh section, advisor of IEEE IS SPS RAS BUET SP chapter, chair IEEE IS SPS EMBS Bangladesh chapter, vice chair IEEE RAS Bangladesh chapter. Now it is our honor to introduce our speaker today, Dr. M. Saif Islam, sir. He is a fellow of IEEE, AAAS, NAI, OSA, SPIE, professor and chair of Department of Electrical and Computer Engineering, University of California, Davis. Dr. M. Saif Islam received his BSc degree in physics from Middle East Technical University, 1994, Turkey, MSc degree in physics from Bilkent University, 1996, Turkey, MS degree in electrical engineering in 1999, and Ph.D. degree in electrical engineering in 2001, both from UCLA. He worked for JDS Uniphase Corporation and Hewlett-Packard Laboratories before joining the University of California, Davis, where he is a professor of the Electrical and Computer Engineering Department. He has authored and co-authored more than 250 scientific papers, organized 30 international conferences and symposiums as a chair and co-chair sponsored by MRS, SPIE, and IEEE, and holds 42 US and international patents as an inventor and co-inventor. He received NF Faculty Early Career Award, Outstanding Junior Faculty Award, and Mid-Career Research Faculty Award, IEEE Professor of the Year and University of California, Davis, Academic Senate Distinguished Teaching Award, the highest teaching honor that the University of California, Davis bestows on its faculties. He co-founded 2 startup companies based on his inventions. Dr. Islam has been serving as an associate editor for IEEE Photonics Journal, IEEE Transaction on Nanotechnology, and IEEE Access. He is an elected fellow of the Institute of Electrical and Electronics Engineers, American Association for the Advancement of Science, Optical Society of America, International Society for Optics and Photonics, and the National Academy of Inventors. Professor Islam's work has covered a broad variety of topics: ultra-fast optoelectronics, materials and devices for harsh environments, synthesis of low-dimensional semiconductor and oxide nanostructures and their applications in devices, ultra-sensitive novel sensors, detectors, circuits, and systems, and fiber optical and RF photonic communication links. Thank you so much, sir, for giving us the opportunity to host you as a speaker of this webinar. I will now request our moderator today, Dr. Celia Shahnaz, to commence the webinar further. Thank you.
Thank you. Thank you, Sanjana, for reading his bio. So while you were reading his bio, to me, it was not listening the bio. It is a celebration of the recognition of such a person. So to me, the way I'm feeling, the contribution and spirit of Professor Saif Islam, hopefully you are feeling the same. So it's not only the feeling, we have to transform our feeling into action in this difficult time. So let us listen to him and prepare ourselves that how we can achieve at least 1% what he has achieved. Then we'll do good. Then we'll do good. So let us take this opportunity in these challenging times, that how we can explore our potential and try to the best of our capacity so that we can come up with some meaningful solutions and use technology to combat the challenges posed by the COVID-19, because COVID-19 is not going to leave us very soon. So it's better how to find out best mechanism to handle it not as a first responder, but we are not first responder. We are technologists. So we have to devise our technology, to find technology, to involve in research and innovation to combat COVID-19. So without further delay, Professor Saif Islam, floor is yours. We want to listen more from you.
Thank you very much, Professor Shahnaz. And thank you, Sanjana. My seminar would be shorter than what you just did. I'm not sure how you managed to collect so much information about all the little things that happened to me. And thank you all for making time. This is late afternoon. I know you had a long day. This is Wednesday in Bangladesh, right? And I'm sure you had a busy day today. So my goal here was to come and meet you all and see how this chapter of IEEE became so much full of energy. And they're not only doing activities in the country, but are also pulling people from all over the globe to join their discussions and interact with them, learn from them. This is really extremely impressive. Here, I would say in the West Coast, we hardly have any activity of IEEE now. And I'm not really hoping our students to be so much enthusiastic about conducting such events. We have a limited number of seminars, and I see students are hardly there. And understandably, they are also a little occupied with so many other problems they're facing now. So I would like to share the screen. Let's see. So I have a couple of slides, which is basically mainly to introduce what is happening in Northern California among number of campuses we have here in this area. Can you see my screen?
Yes, sir, we can see your screen.
Okay, very good. So in Northern California, there are a couple of University of California campuses and a number of industrial, very well-known centers, including Silicon Valley. But north of Silicon Valley, there is San Francisco, which is actually not part of Silicon Valley. And then there is Santa Rosa, Petaluma, and Silicon Valley expanded to Sacramento, Davis, Roseville, and all those areas. So this is really a vibrant place for technologists. And University of California took an initiative. I'll mainly focus on that, and I'll show some of the projects that we are doing. And then we found that entities from outside USA, universities from different countries in the neighborhood also started showing interest in teaming up with us. So one important area University of California wanted to focus on was to see how engineers, in addition to our pharmacists, chemists, and doctors who are working diligently to help in develop the vaccines, but there are other issues that society is facing, and those are some of the issues that engineers could help in addressing. So you probably by now are convinced that infections happen in a number of ways, and we are developing our understanding on that. One way infection happens is if you touch an infected person, or if you're really at a very close proximity to an infected person, or somehow the virus from an infected person moves and flies through the gap you have, which could be tens of feet or even more than that, and eventually reaches you. And if you have sufficient number of those viruses, you get infected. So University of California formed a little committee, gave a small pot of money, and wanted us to address some of those. This talk is going to focus on some of the interesting ideas that people wanted to address. And most of the topics that I'll cover today are about transmission of COVID-19, how we can stop it, how it happens, and what we know about all those now. The kind of contact that happened over time, how people develop their understanding, and how we are now analyzing the data, modeling those, and then for developing new equipment or new protection, what people are doing to address the new understanding that we have. So here I will show a small video that was published by an MIT professor on how when we talk, when we breathe, or when we shout, or when we protest, how pathogens from an infected person goes in the neighboring, in the surrounding area, and how it starts to infect people. So here you're looking at a human being on the left top corner of this video. And you can see how when someone talks within 50 centimeter or close to maybe half a yard, people can spray all the little particles, aerosols, just during the conversation, a simple conversation, the way we are talking now. But when you are talking with some excitement or emotion, you actually go a little far. You go more than a yard, more than a meter, and particles can spread from your mouth very easily all around you. And these are the aerosol particles that could continue to drop on the floor, stick to the wall, on your clothes, and whatever you have around you. Now, if you continue to have vigorous kind of activities such as coughing, sneezing, and or shouting, you actually end up sending those particles maybe 20, 30 feet from where you are. And all these particles are actually full of viruses and little droplets, which contains dangerous pathogens, and those eventually contribute to contaminations. So there is a recent article published in Nature. It shows what happens to all these particles that we emit. So on the left side, you can see some of those settle on the floor, others on the bed rail, locker handle. If you're in hospital and doing all these activities, there are chairs, electrical switches, toilet seats, and a huge number of them eventually end up going to the ventilation or the air circulation plumbing that we have in the room. And then once they are in the HVAC or air circulation plumbing, they can go from one room to the other room because the airflow helps them float in the air and then go to the next room. So these are big problems. So this was published, the video I just showed was published in March 26, 2020. Then on April 7th, another group from Australia basically established the fact that most of the contaminations and infections that happen are happening through airborne virus. A big droplet from our mouth could easily settle on the floor, but the small ones keep going, and you can cover a large area if there is airflow in the room. Same group in May, on May 21st, published a paper and gave guidance on what exactly is happening. So an infected person in a room could, let me use a highlighter. So an infected person could, here could contribute to a lot of droplets and particles. Some of them would settle in the room. Others might end up in the ventilation system. Some would go out of the window. And if the other people in the room are at a safe location, they may not get the infection. If you have UV light to kill the germs, if you have proper ventilation and light, you can avoid infection by an infected person. And based on those guidelines, researchers started working on those. There is one important device in this room, which is air cleaner or air purifier, which is also very essential for keeping a room clean. So basically, you are looking at a number of components in this room, and that involves UV lamp to kill virus, and it involves good ventilation. It involves sensors to see whether you really have a large number of virus particles. You need PPE, you need devices that will capture the virus or trap the virus, some kind of air purifiers. And I was trying to see whether some of the technologies we develop in our lab could help in addressing some of these issues. We probably are not equipped to develop vaccines, but surely these are also important problems that we need to address to minimize the infection. In addition to a hospital room or your own bedroom, there are classrooms that people are trying to now design to address this COVID-19 infection issues. There are offices, then large vessels like cruise ships or manufacturing plants, aircrafts, or places like garment industry that we have in our country. All these are in heavy risk if there are one or two people with infection. The other people in the room could easily get infected if their circulation is not managed properly. So what the University of California did, and let me introduce you to an entity called the Center of Information Technology Research in the Interest of Society, which we in short call CITRUS. This is an entity that was formed between UC Berkeley, Davis, Merced, and Santa Cruz. These are 4 of 10 UC campuses. And UC Davis also has a medical center, UC Davis Medical School, that also is part of this. And so in Northern California, right around the Bay Area, these campuses receive a lot of donations from philanthropists, from rich alumni members. And they wanted us to initiate a COVID-19 research activity plan, and that contributed to developing some ideas about addressing the problems that we could do. So CITRUS responded to COVID-19 and asked us to submit proposals on April 26th, and within around 2 weeks, they started funding some of the proposals that we submitted. I'll talk about a couple of proposals by a number of my colleagues and faculty in different campuses who submitted and got funded. A multi-campus infrastructure to advance telehealth implementation for low-income Californians in response to COVID-19. So this is one of the grants that got funded by CITRUS. It was between 3 campuses, Berkeley, Merced, and Davis. And you can clearly see this is something that is very relevant to what we are facing in our country, in Bangladesh, or any country that requires now to address the health issues of people who are not really capable of taking care of their health in such financial constraints these days. Then the other second project that I would like to talk about is augmented reality video-assisted clinical care. It's basically similar telemedicine kind of project. People could do surgery. People could take a look at, have a deeper dive into the disease and medical conditions through augmented reality, AR, VR, and UC Santa Cruz and UC Davis got involved in that. A project on data scientific approach to coronavirus surveillance. Basically, it's collecting a lot of data and doing a lot of data analysis, AI, machine learning, and eventually using that to understand when or how we should open our campuses, or how we should restart what we already shut down for a long time here. Another project is on identifying and quantifying COVID-19 misinformation, basically all kind of false information and news that really are not based on truth. This can be a very relevant project for Bangladesh. I see a lot of good updates in Facebook, also not that correct information in Facebook, a lot of misinformation and exaggeration by people. Occasionally responsible people also don't check their sources. And so UC Berkeley did a lot of data collection, and they found lots of posting that people do. There are a huge number of misleading information. Like here, you're looking at one of the journal's recent publication that shows rate of misinformation percentage by individual search team. So these are some of the known groups that updates people with whatever is happening in the country, and this is the percentage of their wrong information that they fed to the population. And that's not really good. When people don't get correct information, they make mistakes. In our country, administration misleads people, which is really a big problem. But a lot of people don't have full confidence in the administration, but then people have confidence in groups or different entities, and they also don't a lot of time make mistakes. And there was research, continued research on this topic, and a group from UC Berkeley, received a grant to work on that. Fast deployable low-cost ventilators. I'm sure in Bangladesh, number of groups try to develop similar products. These are extremely important. There was a huge supply shortage of these devices, and this is something a UC Davis team proposed to develop, and I saw their prototype. They're really quick in developing some of the prototypes for testing in the hospital here. At home COVID-19 detection using face mask. So imagine your mask has a sensor which can tell you whether you are at risk or not. And a group at UC Berkeley and UC San Francisco, which is a medical school, together are developing this. Developing a low-cost, scalable, variable output ozone generator. Ozone, just like chlorine, helps in cleaning any surface, anything that are used in hospitals, in homes, or around the patients, and controlled production of ozone, and using it in a very controlled way really is very helpful. On the other hand, I would like to also mention, ozone is very bad for someone suffering from COVID-19. It kills you. It basically destroys your lung. If you're not careful in using it, it could contribute to a huge problem. But a Merced group was trying to develop ozone generator, which is right now very expensive. They're trying to generate it at a lower cost. Open source ventilator. This is something that people are trying to develop. So anyone from anywhere could use the open source code and designs and then build it. Oxygen saturation and temperature sensor. This is very important when we suffer from this kind of infections. Your temperature and oxygen level basically indicates how bad or how terrible the suffering is, and a very low cost, easy, flexible, wearable kind oxygen sensor is always very helpful. So it will constantly monitor your oxygen level and temperature and will update the doctors or connect it to your devices, and will help people in constantly monitoring it. Then safer air in healthcare facilities, which is basically keeping your air safe and clean. And the problem I mentioned, that air-based airborne transmission is a huge problem for large structures or indoor air. And this is something a Berkeley group wanted to address. UC Merced group wanted to develop sensor for detecting antibody for COVID-19, and they're using innovative techniques based on graphene and carbon nanotube. One prototype they developed, I saw it was really impressive. So one project that I got funded was to develop ionization sensor so that we can trap virus and completely remove it from a room, and that way keep the room safe and free from viruses. And I'll talk a little bit about this in simple language. So while we all got funded by this entity, Citrus, there was a Mexico-based university called Tech de Monterrey, or Technology Co de Monterrey, which is one of the largest private schools in Mexico. They have close to 90,000 students, I think 25 different campuses. They found an opportunity to team up with the Citrus-based groups and work together. So what they did is they said they would contribute to a pool of grant money, and they want us to team up with one of their researchers, one of their faculty or research group, and then extend whatever we were planning to do, get a little more money to build prototype, and then get guidance from industry in our neighborhood, and take it to the next level, not only research, but also develop and then build prototype. So this was really a great idea. What I found very attractive is for Mexico, they're still not really at the level where all these Northern Californian universities are, but teaming up with Northern Californian schools and then getting access to the researchers, students, and faculty, and all the labs, they literally benefited a lot. And suddenly you are working at the level where University of California researchers are. And this is something that I would say could be easily implemented by many other countries. Most of the universities in the world right now are very open to work and collaborate with anyone, because the problem we are facing as humanity is huge, and we need collective initiatives. And this is what everyone is looking for. When someone comes with some resource, some grand dollar, and then also wants to team up and then work together, it really helps a lot. So at this stage, this university is now part of many of these grants, and I'm also happy and very lucky to be part of one of the groups that offered me complementary expertise in the activities that I was planning to pursue. So in this slide, I'm showing where this university is, somewhere here in Mexico, Monterey, and California, the place where all these citrus activities are happening right here. So this is really far, far away, but then they're all working. Basically, everyone is at home, but we are all working together, learning from each other. Now, my project was to trap and filter virus. Now, you all probably know by now that virus is in the range of 100 nanometer in size. Here you see a couple of different viruses like influenza virus, rotavirus, Kelly C virus, or SARS virus. And on the right bottom, these are coronavirus. And here I'm showing a scale bar, which shows they're in the range of 100 nanometer. The smallest one is around 60. The biggest one is around 130 nanometer. So you're talking about a particle which is really smaller than anything, any filter that can really capture them. So what people do typically to filter or clean air anywhere is, there are two ways to do it. One is using a HEPA filter. HEPA is high efficiency particulate air filter. And you probably saw those in your air conditioner. After a while, air conditioner kind of has lots of dust in the filter, and you need to replace it when you see a situation like this. And those dust particles are typically in the range of micron, few micron, or tens of micron. And these kind of filters are designed to have at least 0.3 micron filtering capability. So here on the bottom right, I'm not sure if you can see the picture. This right side of this graph shows 0.3 or bigger. So HEPA filter works on this part of this plot. On the left side, everything you see, which is virus or smoke particle or tiny coal dust, those are not really captured by HEPA filter. So anything on the left, which includes all the viruses, cannot be captured by HEPA filter. So what people also do to capture any kind of virus-like particle is ionize particles or ionize a virus so that you can capture it. And what you typically do is you take the virus, turn it into a positive virus or negative virus by adding an ion. And when you have an ion, it's easy for you to attract the ion to another oppositely charged plate or rod or I'm sorry, surface. So the process is you start with a filter like HEPA filter, and you are not really filtering all the viruses, and then you ionize the virus in the second stage, and then you collect the ionized particle, and then end of the process basically gives you clean air. So that's really great. The second process of ionizing helps you in removing all the particles from your room. But there is a danger in ionizing virus or ionizing anything. That danger is, especially when you are in a room with coronavirus patients, you generate ozone when you are ionizing anything, ionizing a dust particle or ionizing a virus. And what is the problem with ozone? Ozone is like Clorox or chlorine. It goes and infects your lung. Your lung is already in infection and it's suffering. You have difficulty breathing. So a healthy lung right here gets infected, and inflammation and other problem eventually makes it worse. It almost like melts like wax when you have ozone in the atmosphere. So ozone is a totally no in a room where you have people with infection. And then other problem is it operates at high voltage. Basically, because it operates at high voltage, you create the ozone, and operation of high voltage basically contributes to a lot of power inefficiency. So ozone is bad for lung, and it really kills the patient. So what do? You are looking for some kind of ionizer which doesn't create ozone. And that's what we propose to do based on some nano engineering or nanotechnology solution. So let me remind you what we are trying to do. We are trying to clean the virus from a room. So there are a couple of devices that we can use. One is a purifier. We can equip someone with a PP, a mask, which can also filter virus. We can have a ventilator, which is equipped with virus filtering capability. Or if we decide to circulate air, if we decide to connect 10 different rooms of a hospital to a single air conditioning unit, we definitely need to make sure every room stops the viruses before they leave the room. And that can be only done through a very high quality filter, which ionizes the virus. And when you ionize, you need to make sure there is no ozone in this ionization process. If you are a designer, if you are an architect of a large building or public places, in future, COVID-19 or similar problems need to be taken into consideration. The plumbing for air conditioning or heating or cooling, all those now need to take this factor seriously into consideration that virus can move from one room. So a room in a corner of a building can easily get contaminated, even though there is no infected people in that room because of this transmission of virus through air. So what we did in our case was to develop a technique which doesn't ionize, doesn't create ozone while ionizing air. And typically what happens is air is full of oxygen gas. You use a device to create some negative ions of oxygen. And it's not possible for you to bring all the viruses to your machine and give them a negative ion. What you do is you send a lot of oxygen, negatively charged oxygen all over the room. And those oxygen would go and give the negative charge to the viruses. And as soon as the virus accepts that negative charge, it then goes and sticks to a wall or to the floor or to something in the room, any surface, rather than flying in the room and floating in the room and then going to the other room or contaminating people who are still healthy. So to ionize anything, you either take an electron away or you add an electron to the atom. If you take an electron away, it becomes a positively charged ion. You add an electron, it becomes a negatively charged ion. It's an easy process for some atoms. It's difficult, really difficult for other atoms. Like here, a group at Stanford used extremely powerful X-ray to ionize some of the big atoms. And especially when they were trying to remove electrons from the core of the atom, it really took a lot of energy for them to do it. So some ions in the periodic table would be really as easy as peeling an orange, very easy to ionize. Others are almost like peeling a coconut, very difficult, really hard. Some are, kind of manageable. But if you use some kind of tools to ionize an atom from the periodic table, you can pick any of the atoms and then you can use some of the tools and you can easily remove the electron and turn it into an ion. And that kind of tools are something that we were looking for ionizing oxygen. So electrical engineers probably know a positive and negatively charged electrode. So here is here's an electrode, here is another electrode. These two are separated by a gap. And if I apply a bias voltage of, let's say, 1000 volt, any air in between will get ionized. But typically air doesn't really get ionized at such low voltage of 1000 volt. You need almost 100,000 volts or even million volt to ionize air. So an oxygen atom would require really, really high voltage to lose its electron. And that's not really good because during this process, oxygen would get ionized, but then oxygen would also turn into ozone, which is something we would like to avoid. So then people developed a technique to cover one of the plates with nanostructures or nanowires. That actually reduced the voltage quite a bit to less than 1000 voltage. And I'll not go into the physics, but the simple thing that happens is this. The field at the tip of a sharp object is inversely proportional to the radius of that object. So if your radius is really tiny, let's say 10 nanometer, your field gets amplified quite a bit. If it is 10 micron, it's not as amplified. So you apply a small voltage, but your field looks like 10 times higher, 20 times higher, because it's a sharp, tiny little object. So the sharpest material on Earth is carbon nanotube. And those who are familiar with this, they probably know it's around a nanometer or 1.3 nanometer in diameter. And if you use sharp carbon nanotube like this and bring it close to a flat parallel plate and apply a bias, you will see the field is so strong at the tip. Any gas like oxygen, carbon dioxide, argon, helium, all these start to ionize at 300, 400, 150 voltage. It's really low voltage. Unlike two parallel plate without this kind of carbon nanotube, which requires 100,000, here you are using less than 1,000 voltage. So that's really good. And when you have such a low voltage, you don't create so much of ozone. You minimize your ozone generation. So I'll skip the theory, but if you have taken some semiconductor physics course, you probably know if you bring a metal in close contact with semiconductor, a lot of interesting activities, things happen, like band diagram changes. And then if you bring a gas atom also close to a metal surface or semiconductor surface, a lot of interesting things happen, but let's skip all those. What I want you to note here is a sharp tip, really extremely sharp tip. And if you bring a gas atom close to this sharp tip, which has only few atoms at the tip, you start to see very interesting phenomena. What happens is these tips are so powerful, they will start to rip all these electrons off, or will give electrons easily, and will ionize these things at fairly low voltage. Let me skip the theory, but now I can give you a sharp tip of metal, and you can also consider using a sharp tip of semiconductor. These are two different materials, and those in semiconductor or metallurgical or chemical engineering or material science world probably know these are different materials. Their electronic structures are different. So here is a metallic sharp tip, really, really sharp. And here is a semiconductor sharp tip. What people found is, although semiconductor sounds like would not be a good choice, actually, because of band diagram, it does a better job in ionizing any gas at low voltage. So we found that theoretically this is possible, but it was difficult for people to implement because sharpening a metal semiconductor tip is not easy. So what we did is we grew them rather than sharpening them. We grew by adding one atom at a time, and this is a bottom-up process. And we found that you actually can take gas and use this kind of really sharp semiconductor tips and ionize ammonia at 8 volt, argon at 9 volt, nitrogen at 5 volt. That's actually really low voltage. Compare it to, thousands of volt or 100,000 of voltage. So when you ionize at such low voltage, you really don't have any ozone in this ionization process. And so based on that, we actually developed some sensors and other devices, and we found that we can ionize a lot of gases at fairly low voltage. Hard gas that will require a couple of thousand voltage, we can very easily ionize them, peel them, and their electrons come off easily. And that is one building block that we are planning to use, generate this kind of sharp tips and then use them to eventually start ionizing gases. And goal is to make the negative ion generation process for cleaning air in the room at fairly low voltage. And the reason we teamed up with the university in Mexico is to understand how we will have to do the airflow, how we'll bring the room air close to this machine, and how the viruses would eventually be captured, and what else we could do to eventually minimize the virus number per cubic unit volume, and eventually capture them, kill them, or remove them from the room. So the goal I had today was to show you that there are opportunities for engineers, and I just showed one kind of activities we do, which involves a lot of physical development of devices or materials or tools to address this problem. But then once you start using those there would be data and information, and there'll be patterns, and there are observations that you have to analyze, and based on that, understand what the optimum ways are to eventually make use of all these to do even more efficient jobs. And the fact that a neighboring country teamed up with us and they wanted to strengthen their capabilities shows how the world should address this problem together, how we should learn from each other, and how we can keep ourselves busy in this tough time. And that way, the depressed people all over the world eventually will come out of this huge problem. Thank you very much for your attention.
Thank you, Prof. Saif Islam, for sharing amazing initiatives, and I should say the research that is got funding for deploying technology for the local community. That's great. The data science for surveillance, that COVID misinformation classification, the ventilator, oxygen saturation maintained, and especially your work. What I found that although you were targeting this COVID-19 situation, but this work is so scalable and so sustainable, even if you can use it even after the pandemic is over in our normal life. So that's actually the far-reaching impact of your research. So you'll be happy to know that we have at this moment 67 participants from Bangladesh, different universities from Bangladesh, of course, majority from BUET and other parts of Bangladesh. And the most important thing is that the rural areas of Bangladesh, Maulana Bhashani, Kushtia, like this. That's the thing, people, we are keeping, and also different states of India. India has 12 sections. So I can see many of my friends from different states of India and also different sections of Pakistan. And you will be amazed to know that there are participants from Bhutan, and I said Australia and USA. I thank every one of them. Now you are free to ask question to Professor Saif Islam. Please write your question, or you can open up we can unmute you and you can ask question. So I can see one question. Can such nanostructure be implemented whose shape can be changed dynamically according to the situation of its environment?
So that's really very interesting capability. I'm not sure how you can dynamically change the shape of nanostructure unless they're really flexible. But what is important for this particular application is a very sharp tip, really super sharp, so that the diameter at the tip is as small as possible, and the field or the strength of ionization that you create at the tip is inversely proportional to the diameter. If you can play with the diameter, if you can reduce or increase it, depending on the situation, I'm not sure what kind of material you're talking about, I think it would offer interesting opportunities for other things. Let me also mention, I never really started this work to address COVID-19 problem. I have been doing it for some time. I was trying to clean air in coal-fired power plants, or air in a room where you have all kind of indoor pollution. But if you have materials that can dynamically change the shape or characteristics, I can see interesting lot of opportunities that would be possible. Please contact me if you think you have done work on that kind of materials.
Yes, thank you, Prof. Saif Islam. And we have another very brief question. Is the device only applicable to the COVID case, or we may hope it for other virus or harmful bacteria? Hussein, are you asking about his device ionizing to trap virus?
Yes, ma'am.
Saif Islam, going on.
The device is capable of ionizing anything, but big particles can easily be filtered using a regular filter that we see all over in different devices like air conditioning and other units. But problem is the small particles, which is below 0.3 micron, or which is smaller than 0.3 micron, which is 300 nanometer, and virus is 100 nanometer, or even smaller than 100 nanometer. So that one requires ionization. But then when you ionize, you actually ionize big particles, you ionize anything in the room, and you capture them. And good thing about ionizing filter or ionizing devices, they go and stick to a surface which you just wash or wipe, unlike filters that are used in air conditioning. Once they're dirty, you just have to replace that. So big or small particles can be ionized and they can be captured equally efficiently.
Yeah, thank you, sir.
Another question, can silicon nanowire be used here instead of CNT?
Okay, so that's a great question. Now, both CNT and silicon nanowires are bad choice because so there is a process that material scientists should understand. It's called desorption. Ionization process is a very harsh process. What happens is you have a sharp tip and all these oxygen atoms or other gas atoms are just walking or flying around it. And some are flying so fast, they go and make the silicon tip less sharp, and silicon tip slowly gets dissolved, or actually silicon tip might disappear. So what we did subsequently, once we saw that silicon tips are not the best candidates for it, we actually started working with hard materials, such as aluminum nitride, such as gallium nitride, or diamond-like carbon. Those are harder material. And my goal was eventually to use boron nitride, which is very close to diamond and very hard and would not get dissolved or evaporated. Carbon nanotube is also very hard material, but then when an ion flies and hits it with such high speed and energy, it slowly also melts and dissolves. So none of the materials I showed here are the right candidate if you want to make a sustainable filter for months and years. You need other materials that are more durable, and those materials exist.
There is a thank you for your insightful scientific guideline for choice of materials. And there is a common question because you are researchers, people think that you are a philosopher also, and you can give vision. And I know that.
No, I'm not a philosopher. That was a wrong observation. I'm an engineer, engineering professor.
Of course. And engineers and philosophy now working together nowadays. So that's why people are not telling it is STEM, STEM. People are not at all telling it. People are telling it is STEAM. People are bringing arts into it to make it more versatile and to reach it to more people. Okay. So people are seeing it as you as a more versatile. That's why they have asked question. What steps should be taken to improve the COVID-19 condition of Bangladesh?
So that's
your
really
suggestions.
It's a loaded question, and it's a huge problem.
That's why I have given that summary, preamble.
So by now we all are convinced this is not really a little simple problem. This is I don't think anything like this happened in the recent past, maybe in the last 100 years. The magnitude of the problem is big, and we only can all focus on one small aspect of it. Obviously, we also need to see the bigger picture. Big picture basically tells us this is a huge problem. We all need to work collectively, come up with a collective plan, and work together. Every society is a little bit different, but then this is a global problem. So the whole world needs to work together, but then within a country, people, doctors, engineers, scientists, researchers, people who do farming, we all need to be on the same page and work together. I think everyone probably knows something very well. We just need to figure out how we can contribute using that. If you are a researcher, continue your research, see how you can solve the problems that people are facing now. If you think you can't really get access to a research lab or do research, maybe you know how to communicate and make people aware of the problem, and that way help people not cause more contaminations and infections in the society. There is no way we can address this with a 1 or 2 sentence answer, but we all have responsibilities. Everyone could do something, and I think a coherent plan by every society can offer guidance to every citizen to figure out what they could do to address the giant problem we are facing now.
So there is another inquisitive question. Are these recommended for closed rooms? That means AC rooms, or only we can use it for open rooms also? Say non-AC rooms.
So if you're outside, if you're not really in an enclosed structure, I think you are at a smaller risk. There is basically, if you keep the distance, adequate distance, you don't have too much of issue. There is always some kind of air circulation outside the buildings. But most of the contaminations and big problems where even doctors die, nurses die, or you have a family member at home in one room, and pretty soon everyone in the same home are all infected. So those are happening and causing a lot of infections. Or you are eating food in a restaurant, or you are in the same space, enclosed space, and the air is not cleaned, and you end up getting the infection. So we are looking at the enclosed space problem. Outside, you can't clean the whole universe. This is huge, but and most of the time we are inside, we are indoor, and we need to address this indoor issue more urgently.
Thank you. So actually, I like to inspire others, saying that recently around March, we submitted a proposal to build robots for disinfection public places. But there are different rules of applying or throwing liquid to the public places. So what we are targeting, we want to disinfect the university campuses. Say IEEE Bangladesh section has 51 student branches, and we are targeting that we will give training, online training to the students, how to build this disinfection robots, so that maybe from 51, at least 10 designs will come, and we'll come up with one of the unique and one of the best design. And we can team up with the North City Corporation. We have already contacted the mayor, so that we can launch this project in the product. At least we can try starting with our campuses. Although our campuses are empty, but still there are a few office works are going on, and many people are going to the office for a short period. Hope it is very much needed, and it will be needing also after the pandemic. This mega plan we have taken, and we are starting from 5th July. And I welcome all of you for your valuable contribution in that project. We have received only $5,000, but it's not the dollar, it's a vision that what you can do starting from your very own campus. So similarly, I just share what we did, and many of our students, Professor Saif, are through these IEEE webinars that we started around March. I really inspired them to at least involve themselves in some projects. Many of them are now designing ventilators, and many of them are now involved in designing the automatic hand sanitizer. So these are the things, and I'm also telling them, that there are village schools. If you keep on doing it and you transform your project into product, that even after the lockdown, you can deploy these sanitizers to the school where they do not have anything, no soap, nothing. So it will be our habit, and it will be our culture. So these are the things, hope our students We did our level best to engage our students. I just shared that what they're doing. And as a researcher, what I'm doing actually, I'm handling that X-ray. You know, there are only 400 X-ray images of COVID publicly available because we are not, our hospitals are not allowing us to have those X-ray images but we work with what are the X-ray image available to us. So we are applying deep learning for detecting COVID or non-COVID. Hope we can come up with an app that could help the doctors to detect COVID or non-COVID very quickly. So these are the plans. So this is not only my plan or our plan. Here there is 75 participants from almost many countries of this Asia Pacific and beyond Asia Pacific. This is just for resource sharing. You can communicate with each other, and we can employ those techniques by sharing those resources. So Professor Saif Islam, I really felt amazed listening to your deionizing procedure for trapping the virus. This is very important for our hospitals because many of our ICU heads died. So I will immediately talk with Dhaka Medical College Hospital and with our researchers so that we can at least start thinking about implementing it. Thank you, Prof. Saif.
Let me mention something. There is a commercial product available that sells at around $1,000 or $800. And you can buy those, but those are good for a healthy person's office or home. But for coronavirus patients, this is not safe. So we are working on making it safer in terms of ozone generation.
Yes.
And that will make it safe for every place. That's the goal.
I got the point.
Thank you very much. Thanks to everyone for making time. I am really impressed to see you can bring so many people together from so many different places. That shows we can be hopeful. And I'm hoping one of you eventually one day would be a political leader in our country or wherever you are from. And hopefully you'll learn from the way a number of countries are working together to eventually solve this common problem. I'm hoping Bangladesh should also come up with a similar plan to fund our university researchers, our professors and students, and also team up with international entities to address this global problem.